and welcome to the 5th video of the ISTQB Certified Tester Foundation Level Preparation course. My name is v3, and I'm a creative manager at Exactpro. Today we will cover Chapter 5, Test Management. This chapter calls for a brief overview of what we have already discussed in the first video, and that is the question of independent testing. So let's go over it one more time. A certain degree of independence often makes the tester more effective at finding bugs due to the difference between the author's and the tester's cognitive biases. But again, I want to reiterate that independence is not a replacement for familiarity, and developers can test their code and efficiently find defects. Projects usually have multiple test levels, and independent testers could be handling some of those levels, with the active participation of developers at lower levels. Let's quickly review the degrees of independence in testing one more time. Number 1, no independent testers. That would be developers testing their own code. Number 2, independent developers or testers within the development team or the project team. This could be the developers testing their colleagues' products. Number 3, independent test team or group within the organization. Number 4, independent testers from the business organization or user community or with specialization in specific test types. And number 5, independent testers external to the organization, either working on-site, that's in-house, or off-site, that's outsourcing. What are the benefits of test independence? Independent testers are likely to find different kinds of failures compared to developers. An independent tester can verify, challenge, or disprove assumptions made by stakeholders. Independent testers can report in an objective manner about the system without feeling pressure of the company that hired them. And what are the potential drawbacks of test independence? Isolation from the development team may lead to a lack of collaboration with the development team, or even an adversarial relationship with the development team. Developers may lose a sense of responsibility for quality. Independent testers may be seen as a bottleneck, and independent testers may not have all the important information. Successful test process needs to be thorough in order to avoid chaos. And that brings us to today's topic, which is test management. According to the glossary, test management is the planning, scheduling, estimating, monitoring, reporting, control, and completion of test activities. In order to understand how the test process is managed, it is important to know the roles involved and their typical tasks. The key roles here are of a test manager and a tester. The test manager assembles and leads the team, defines scopes, distributes resources, and makes sure that the process runs smoothly and achieves results. He is also an advocate for his team, responsible for feedback and motivation. The tester, on the other hand, designs and executes tests, guaranteeing a high quality of the final product. Both the tester and the test manager have to be able to compare results, compile reports, and assess the efficiency of the testing process. In a nutshell, test managers are responsible for strategies and tactics, whereas testers mainly focus on practical work, but in some areas their responsibilities may overlap. Of course, these are brief descriptions of their tasks. The presentation you will see later will contain all of them as per the ISTQB syllabus. So both of those roles are responsible for planning, each at their own level, of course. This activity is crucial. Without it, testing becomes a spontaneous process, uncontrolled and impossible to evaluate. And even though we can find some bugs this way, the lack of reliable control will soon turn the whole process into a nightmare, especially for a large and complex project. A test plan describes activities for every step of the process and is determined by the company's test strategy, SDLCs, and other factors, including the availability of resources. It is recurrent and performed regularly throughout the duration of the project. As the project continues, more information becomes available and more detail can be included in the test plan. In regard to the documentation standards, there will be a master test plan as well as plans for test levels. There could also be separate plans for functional and non-functional testing. Test planning may include the following. Number 1. Determining the scope, objectives, and risks of testing. Number 2. Defining the overall approach of testing. Number 3. Integrating and coordinating the test activities into the software lifecycle activities. Number 4. Making decisions about what to test, the people and other resources required to perform the various test activities, and how test activities will be carried out. 5. Scheduling of test analysis, design, implementation, execution, and evaluation activities, either on particular dates, for example, in sequential development, or in the context of each iteration, for example, in iterative development. 6. Selecting metrics for test monitoring and control. 7. Budgeting for the test activities. And 8. Determining the level of detail and structure for test documentation. And then there is test strategy, which is documentation aligned with the test policy that describes the generic requirements for testing and details how to perform testing within the organization. Unlike a plan, test strategy provides a generalized description of the process, usually at the product or organizational level. Here is a list of the most common test strategy approaches. Analytical. It is based on the review of some factors. Risk-based testing is an example of an analytical approach. It is usually conducted in the form of a stakeholder meeting where everything that could potentially go wrong gets discussed and identified. All of those risks become targets for test cases. Model-based. Here, tests are designed based on some model of a required aspect of the product. Examples of such models include business process models, state models, and reliability growth models. Methodical. It relies on making systematic use of some predefined set of tests or test conditions. In other words, our experience dictates the basic principles of this approach. Process compliant or standard compliant involves analyzing, designing, and implementing tests based on external rules and standardizations. This approach is prevalent in standard-reliant industries like aviation and medicine. Directed or consultative is primarily driven by the advice, guidance, or instructions of stakeholders, business domain experts, or technology experts. Regression-averse helps to avoid regression of existing capabilities. This test strategy focuses on extensive automation of regression tests. Here we check the existing functionality first to make sure that the new additions didn't break anything. And reactive. It focuses on the test events occurring during test execution rather than on pre-planned ones. If the component under test is unstable, it warrants more immediate in-depth testing. A project might choose one or a combination of several strategies, best suited for its needs. So the test strategy is a generalized test description of the test process. The test approach, on the other hand, tailors the test strategy for a particular project or release. The test approach is the starting point for selecting the test techniques, test levels, and test types, and for defining the entry and exit criteria. Entry criteria is the set of conditions for officially starting a defined task. Answering the following questions helps to understand if we have everything necessary to begin. Do we have the requirements? What about test items that met the exit criteria for previous test levels? Is the environment set up? Do we have the necessary tools to test? Do we have technical and human resources ready? Do we have an approved date? If entry criteria are not met, it is likely that the activity will prove more difficult, time-consuming, costly, and risky. Exit criteria is the set of conditions for officially completing a defined task. And it has its own set of questions. Have all the planned test cases been executed? Have we achieved the planned level of coverage? Are there any raised high-risk bugs that are still unresolved? What about the level of quality characteristics? Are they sufficient? Are we at the deadline? After that, we can create a test execution schedule. Once the various test cases and test procedures are produced and assembled into test suites, the test suites can be arranged in a test execution schedule that defines the order in which they are to be run. This schedule should take into account such factors as prioritization, dependencies, confirmation tests, regression tests, and creating the most efficient sequence for the execution of those tests. Ideally, test cases should be ordered to run according to their priority levels, executing the test cases with the highest priority first. However, this may not be wise if the test cases or the features being tested have dependencies. If a test case with a higher priority is reliant on a test case with a lower priority, the lower priority test case must be executed first. Also, we need to allocate sufficient time for confirmation and regression testing. Estimating the schedule happens simultaneously with the test effort assessment, which predicts the amount of test-related work needed to meet the objectives for a particular project or iteration. Factors influencing the test effort may include product characteristics, development process aspects, personal skills, and the test results. There are a number of estimation techniques used to determine the effort required for adequate testing. Two of the most commonly used ones are: number one, the metrics-based technique. Here we estimate the test effort based on metrics of former similar projects or typical values. Analyzing metrics can be as simple or sophisticated as you make it. The simplest approach is to ask, how many testers do we typically have per developer on a project? A more reliable approach involves classifying the project in terms of size and complexity and then comparing this to past projects. Another simple and reliable approach is to look at the average effort per test case in similar past projects and to use the estimated number of test cases to estimate the total effort. Sophisticated approaches involve building mathematical models in a spreadsheet or other tools that look at historical or industry averages for certain key parameters: number of tests run by a tester per day, number of defects found by a tester per day, etc., and then plugging in those parameters to predict duration and effort for key tasks or activities on your project. Number two, the expert-based technique. That is estimating the test effort based on the experience of test task owners or other experts to develop a structure for the project. The idea is to draw on the collective wisdom of the team to create your test estimate. The next thing we need to do in the test management process is establishing test monitoring and control. Test monitoring is the activity that checks the status of test activities, identifies any variances from planned or expected, and reports status to stakeholders. The purpose of test monitoring is to gather information and provide feedback and visibility about test activities. Information to be tracked may be collected manually or automatically and should be used to assess test progress and to measure whether the test exit criteria are satisfied. Test control is the activity that develops and applies corrective actions to get a test project on track when it deviates from what was planned. Test control describes any guiding or corrective actions taken as a result of metrics gathered and reported. These actions may cover and affect any software lifecycle activity. Tests can also be reprioritized, test schedule can be changed, and entry and exit criteria can be adjusted. Let's look at some of these metrics. 1. Percentage of planned work done in test case and environment preparation. 2. Test case execution, number of test cases passed and run, failure rate, and so on. 3. Defect information, defect density, defects found and fixed, failure rate, and confirmation test results. 4. Test coverage of requirements, user stories, acceptance criteria, risks, or code. 5. Task completion, resource allocation, and usage and effort. And finally, the cost of testing. Here we compare it to the benefit of finding the next defect or to the benefit of running the next test. During test monitoring and control, the test manager regularly issues test progress reports for stakeholders, providing them with the necessary information. There are two types of reports: progress and summary. Test progress report is a type of test report produced at regular intervals about the progress of test activities against a baseline, risks, and alternatives requiring a decision. It should be sent periodically and may include the status of test activities and progress against the test plan, factors delaying the progress, testing planned for the next reporting period, and the quality of the test object. Test summary report is a type of test report produced at completion milestones that provides an evaluation of the corresponding test items against exit criteria. It should be sent at the end. Here is what it may include: information on what occurred during the test period, deviations from the plan, the status of testing and product quality, blocking factors, metrics of defects, test coverage, residual risks, and reusable test work products produced. These reports should be made clear and understandable for the intended audience. All the stakeholders need to know the scope and the result of testing in order to make informed decisions about the software. In order to properly support testing, configuration management is needed. It helps us to make sure that all test items are uniquely identified, version controlled, tracked for changes, and related to each other. All items of testware are uniquely identified, version controlled, tracked for changes, related to each other, and related to versions of the test item. All identified documents and software items are clearly referenced in test documentation. Configuration management is a discipline applying technical and administrative direction and surveillance to identify and document the functional and physical characteristics of a configuration item, control changes to those characteristics, record and report change processing and implementation status, and verify that it complies with the specified requirements. The purpose of configuration management is to establish and maintain the integrity of the component or system, the testware, and their relationships to one another through the project and product lifecycle. Let's talk about risks. One of the most essential activities of the test team is to mitigate them. Risk is a factor that could result in future negative consequences. At this stage, we classify them into product and project risks. Product risk is a risk impacting the quality of a product, and it involves the possibility that a work product, a specification, component, system, or test may fail to satisfy the legitimate needs of its stakeholders. When the product risks are associated with the specific quality characteristics, for example, functional suitability, reliability, performance efficiency, usability, security, compatibility, maintainability, or portability, they can be also called quality risks. Let's say we're releasing a new matching engine. The deadline is near, but there are some bottlenecks where the response time is inadequate. The project team makes a decision to deploy it despite the shortcomings. They stick to the timeline, but the end users might observe latency deterioration. This is a product risk. A project risk is a risk that impacts project success. It is a situation that may have a negative effect on the project's ability to achieve its objectives. We can review the matching engine example again. Now the project team decides to address the response time issues. As a result, the end product will satisfy the stakeholders' expectations, but they may miss the deadline or exceed the budget. That would be a project risk. Risk-based testing is a kind of testing in which the management, selection, prioritization, and use of testing activities and resources are based on the corresponding risk types and risk levels. A risk-based approach to testing provides proactive opportunities to reduce the levels of product risk. It involves product risk analysis, which includes the identification of product risks and the assessment of their likelihood and impact. The resulting product risk information is used to guide test planning, the specification, preparation, and execution of test cases, as well as test monitoring and control. Analyzing product risks early contributes to the success of a project. Finding defects is not enough. All of them should also be logged. The way it is done may vary, depending on the context of the system under test, the test level, and the software development lifecycle model. But every defect identified should be investigated and should be tracked from its discovery to resolution. This may include correction of the defect and successful confirmation testing, as well as deferral to a subsequent release or acceptance as a permanent product limitation. In order to successfully deal with bugs, an organization should establish a defect management process, which includes a workflow and rules for classification. This process must be agreed on by all those participating in defect management. In some organizations, defect logging and tracking may be very informal, although a casual attitude toward defect tracking might have negative effect on the process. If bugs are raised only verbally, then what are the chances that some of them will get overlooked? If a bug gets fixed but never logged, then there's a chance that the traceability is lost, and we don't know the defect's origin. Who's to say that the same bug won't get introduced in all of the consecutive builds? So for the sake of informality, bugs get lost and causes get uninvestigated. There has to be a centralized bug tracking system to avoid all of that, as well as to help evaluate the QA department efforts. Defect report is documentation of the occurrence, nature, and status of a defect. Typical defect reports have the following objectives. Provide developers and other parties with information about any adverse event that occurred, to enable them to identify and to isolate the problem with a minimal reproducing test, to correct the potential defects, or to resolve the problem. Provide test managers a means of tracking the quality of the work product and the impact on the testing. For example, if a lot of defects are found, the testers will spend a lot of time reporting them instead of running tests, and there will be more confirmation testing needed. Provide ideas for development and test process improvement. This concludes the 5th chapter of the ISTQB Foundation Level Preparation course. Good luck with your studies, and I'll see you at Chapter 6.